Hello again. This is Math 2233 coming to you from the College U page. The title of this lecture is Vector Valued Functions and Space Curves, and I remind you to be an active learner as you review this video. Paths of objects moving through space, like the jet planes pictured here, can be described by vector functions. We'll see how to use these vector functions to determine whether or not such two objects will collide. The functions that we've been using so far have been real valued functions. We now study functions whose values are vectors, because such functions are needed to describe curves and surfaces in space. We'll also use vector valued functions to describe the motion of objects through space. In particular, we will use them to derive Kepler's laws of planetary motion later. Vector valued functions can be used to model paths in three-dimensional space. These paths are space curves, which can be used to model shapes and motion. For example, in nuclear reactors, scientists use equipment to produce energy from nuclear fission. Nuclear fission depends on finding the exact paths of nuclear particles through space. Such paths can be modeled using vector-valued functions. Biologists will sometimes track birds during migration to find their migration routes and destination. The set of points that represents a bird's location over time is a vector-valued function and approximates a space curve. When facing a strong crosswind, an archer must consider distance from the target, vertical aim and horizontal aim. Due to the crosswind, the arrow's flight must be modeled with a curve in space instead of a curve in a plane. Vector functions and space curves. In general, a function is a rule that assigns to each element in the domain an element in the range. A vector-valued function or vector function is simply a function whose domain is a set of real numbers and whose range is a set of vectors. We're most interested in vector functions R, whose values are three-dimensional vectors. This means that for every number t in the domain of R, there's a unique vector in V3, denoted by R of t. And if f of t, g of t, and h of t are the components of the vector R of t, then f, g, and h are real-valued functions called the component functions of R, and we write it this way. R of t is equal to pointy bracket f hat of t, g hat of t, h hat of h of t, no hats, or f of t I, g of t j, h of t k. We use the letter t to denote the independent variable because it represents time in most applications of vector functions. So here's a problem for you to consider. What is the domain of the following vector-valued function? R of t is equal to pointy bracket t cubed, comma, ln 3 minus t, and the square root of t. You know what to do. Let's see how you did. So if R of t is as before, then the component functions are these, and these. By use of convention, the domain of R consists of all AST for which the expression for R of t is defined. So these expressions are all defined when 3 minus t is bigger than 0 and t is bigger than or equal to 0. Therefore, the domain is the half-open interval, closed bracket, 0, comma, 3, open bracket, or open parentheses. We can also talk about limits. The limit of a vector function R is defined by using limits of its component functions as follows. So if R of t is pointy bracket f, g, and h into pointy bracket, then the limit as t tends to a of R of t is equal to pointy bracket and the limit of each component as t goes to 0, provided those limits exist. Note that this definition is equivalent to saying that the length and the direction of the vector R of t approaches the length and direction of the vector L. And we could use epsilon delta definitions here, but we would have to use the metrics or norms associated with vectors to do that. There's a problem. Find the limit as t goes to 0 of r of t, where r of t is equal to this expression. You know what to do. Let's see how you did. So we take the limit of each component. The limit as t goes to 0. This one is going to be 1. The limit as t goes to 0 of this one, the exponential will dominate, and that will be 0. And this limit was one of the first ones you learned in Calculus 1, and that limit is going to be equal to 1. So this goes to 1, so that is just I. This goes to 0, so the j doesn't show up. And this goes to 1, so that is 1k. So this is I plus k. Now we say a vector r is continuous at a if the limit as t tends to a of r of t is equal to r of a. And so we can also see that r is continuous at a if and only if all of its component functions are continuous at a. Now, there is a close connection between continuous vector functions and space curves. Suppose that f, g, and h are continuous real-valued functions on an interval I. Then a set of points C of all points in x, y, and z, these are ordered triples in space where x is equal to f of t, g of t, h of t, as t varies throughout t is called the space curve. And you can see that you have a space curve here. And these equations are called the parametric equations of C, and t is a parametric value, or is called the parameter. We can think of C as being traced out by a moving particle whose positions at time t is f of t, g of t, h of t. Now that means it does have an orientation, and you discuss this a little bit in Calc 2. So it starts somewhere and can end somewhere. Now, if we consider the vector function r of t equal pointing bracket f, g, and h into pointing bracket, then r of t defines the position vector of this on C. And so we're talking about having the vector that's tracing out that curve, but we're putting the end of the vector at 0. So the point of the vector is this. And that also defines a space curve that's traced out by moving the tip of the vector. Describe this curve defined by the vector function r of t is equal to pointing bracket 1 plus t, comma, 2 plus 5t, comma, 1 plus 6t. You know what to do. Let's see how you did. Well, the curve parametric equations then are x is equal to 1 plus t, y is equal to 2 plus 5t, and this is z is equal to minus 1 plus 6t. So you see that this is the line segment. This is a parametric equation of a line passing through the point, parentheses 1, 2, minus 1, and parallel to the vector pointing bracket 1, 5, 6 into pointing bracket. Alternatively, we could observe this function can be written in this form, where this is the initial point on the tip of the vector, and this is the direction of the vector as it moves through time. So this is the vector equation of a line given by that function. So this is a line. Plane curves can be represented by vector notation. For example, the curve given by x is equal to this and y is equal to this could be described as the two-dimensional vector equation given by this in I and j, and this using the pointing bracket notation. And I and j, as always, represent the standard unit vectors in the direction of I, or in the direction of x, and j in the direction of y. Okay, let's do another example, maybe a more interesting one. Let's sketch the curve whose vector equation is given by r of t is equal to cosine of t times I plus sine of t times j plus t times k. You know what to do. And we'll see how you do when we resume this with the continuation video. But in closing for now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all until you watch the conclusion of this video. See you then.